So now we're going to look at in more detail at the two different cases of a changing magnetic flux in which an EMF is induced. So the first is when we have a conductor which is moving through a magnetic field. And so in this situation, we can see that the induced EMF is caused by a charge separation in the conductor. So let's see what this means. We have a U-shaped wire and then a conducting rod moving to the right through this magnetic field, which is pointing into the page. So we're going to look at positive charges, but remember, in reality, the positive charges in the rod aren't going to move. It's the electrons that are moving. So by using the right-hand rule, we can determine which way the magnetic force is going to act on these particles inside the rod. Because the particles are moving, so a magnetic force acts on moving charged particles. So using the formula, V cross B, we can determine that the positive charged particles in this moving rod will be pushed upwards towards the top, here at point A. And so the positive charges are going to start accumulating at this point A. And then as the charges accumulate, they're going to set up an electric field, which is pointing downwards. So now we have two opposing forces in this moving rod. We have the magnetic force, which is pushing particles upwards, and this electric force, which is pushing them downwards. And so eventually, these two forces will reach equilibrium, and they'll be equal to each other. So at this point, we have QE, the electric force, is equal to QVB, the magnetic force on these charged particles. And so we can find the potential difference across this rod from point A to B at this point by multiplying the electric field times the rod's length, L. So from here we can see that the electric field is equal to VB when these forces come into equilibrium. So multiplying that by the length of the rod, we get that the potential difference across it is VBL, the velocity of the moving conductor times the magnetic field times the length of this moving rod. And so this rod can maintain this potential difference across its ends, which causes an EMF. So we call this the motional electromotive force, and so it's going to be equal to VBL in this case of a moving rod through this magnetic field. So it's going to create a current in the circuit from A to B. And again, we can find the direction of that current using Lenz's law. Because if the current is from A to B, counterclockwise around the circuit, then using the right-hand rule on this conductor, we can see that the magnetic force on it is going to be to the left, which opposes the original motion, which is the cause of the induced EMF. And so remember, Lenz's law, the induced current is going to oppose the original cause of the induced EMF. And so we've just been talking about this little rod here moving through this magnetic field in a U-shaped wire. But it turns out we can come up with an equation to use in any case of motional EMF. So for any closed conducting loop of any shape moving in any magnetic field, we can use this expression to find the induced EMF. We take the cross product of the velocity and the magnetic field, and we dot that with dl. And so if we integrate over the total length of whatever the moving part of the conductor is, then we'll get the induced EMF. So you can use this with any shaped conductor, or even, say, a conductor which is rotating through a magnetic field. So now let's look at the other case when we have a stationary conductor, but a changing magnetic field through that conductor. And so in this case, we can't say that the induced EMF is caused by the magnetic force separating the charges, because there is no magnetic force on the charged particles inside the conductor. Since it's a stationary conductor, they're not moving, so there can't be a magnetic force on them. So in this case, we say that the changing magnetic flux causes what's called an induced electric field in the conductor. And then this induced electric field in the conductor then exerts a force on the charged particles, which causes them to move around and make that induced EMF and current. And so this induced electric field is a bit different from regular electric fields that we've been working with so far. So we say that this induced electric field is non-conservative. So this means that if we have a charged particle and it goes around the loop once in a closed, just goes around the loop once, the induced electric field is going to do work on that charged particle. Remember, in a regular electric field, if a charged particle moves in a closed loop and comes back to its starting position, the total work on it is going to be 0. But in this case, the electric field is doing work on a particle when it moves around and comes back to its starting position. And so the work that the induced electric field does on a charged particle as it moves around this loop once is going to be the integral of the dot product of the electric field times dl. And this circle is here because we're integrating around the whole entire loop. And so this times q, the charge of whatever particle we're moving, is going to be equal to the work that the induced electric field does on the particle as it moves around the conductor once. And since EMF is work divided by charge, then we can just get rid of the q, and this expression is going to be equal to the induced EMF in the circuit. So again, this induced electric field is different because we know that for a regular electric field, if we took the integral of the electric field dot dl around a closed loop, it would be equal to 0. But in this case, it's equal to the induced EMF. And so this kind of weird electric field is also called a non-electrostatic field. And since it is non-conservative, we can't define a meaning of electric potential in this conductor. Since, let's say we take this point, and it has a value of potential, but then if we move around the loop once, the electric field is doing work on a charged particle. So when we come back to this point, the potential is higher. It's changed value. So how can we have different values of potential at a single point? Well, we can't, because the potential here has no meaning in this non-conservative electric field.